If an interviewer asks you to design a system that handles 10 million requests per day, how do you start? How you answer this specific prompt separates a standard senior software engineer from a solution architect. To master this, we are going to use a mathematical, step-by-step framework to build a complete architecture diagram from scratch. The most common mistake candidates make is falling into this tech stack trap, immediately blurting out tools like Kubernetes or Kafka without any context. Interviewers don't want a list of technologies. They want to see a structural process that proves you can identify and solve bottlenecks before they break a system. Step 1 is to clarify the requirements before you draw a single box on the board. You must establish the operational boundaries by asking, are these mostly read or write requests? Is the traffic global? Is strict data consistency a requirement? Once you have those answers, step 2 is calculating the average requests per second. 10 million daily requests divided by the seconds in a day gives us roughly 120 average RPS. However, traffic is never evenly distributed. If you only design for that average line, a single spike during a busy hour will crash the entire stack. To build in enough headroom, we apply a standard multiplier. Multiplying our average by 8 gives us a target of approximately 1,000 peak requests per second. This 1,000 peak RPS metric is now your mathematical foundation. Every design choice you make from this point forward must solve for this specific target. Step 3 is sizing your compute layer by testing its capacity against that 1,000 RPS. You have to determine if a single standard server can handle all 1,000 requests. If we assume one server handles 250 requests per second, we need a cluster of 4 servers to stay online. With multiple servers, we now add a load balancer to distribute the incoming traffic flow evenly across the cluster. Step 4 is scaling the data layer. We apply that same capacity test to our database. If one database instance cannot sustain 1,000 requests per second, you must include read replicas to offload pressure. To prevent the database from becoming a bottleneck, we introduce a caching layer to intercept repeated requests before they hit the disk. By checking capacity against your target metric at each step, you can justify the addition of every component in the stack with actual data. Step 5 is offloading heavy assets to ensure the core API only handles the logic it was built for. Static files like images, videos, or PDFs should be routed directly to a content delivery network. This keeps that high-volume traffic off your main compute nodes entirely. You also need to address long-running tasks. If a user uploads a large file, the API should not sit idle while it processes. Instead, you use a message queue. The API offloads the job to the queue, and dedicated workers process it in the background, allowing the API to immediately handle the next request. Finally, step 6 is proving your system is ready for a real production environment through observability. By adding a monitoring and logging layer over the entire diagram, you ensure that if any of these components fail, you have the telemetry to see exactly where and why. Accounting for background tasks and system health tells the interviewer you are designing for the reality of maintenance and scaling, not just a theoretical model. At this point, you have a complete, logically defensible architecture on the board. But here is the most important part. Don't use this full diagram if the math doesn't require it. What if the requirements only worked out to 80 peak RPS? If you only have 80 requests per second, the complex system on the left is a failure of judgment. A single server and a simple database, as shown on the right, is the correct cost-effective answer. A true solution architect's job is to identify the specific bottleneck and remove it with the simplest possible solution. Use the math to drive your design, and you'll ace the interview.